Hi, my name is Ioana Bica and I'm a PhD student at the University of Oxford and the Alan Turing Institute. In this tutorial, I'll present our work on the time series deconfounder, a method that can be used for estimating treatment effects over time in the presence of hidden confounders. The aim of this work is to be able to obtain unbiased estimates of the causal effects of treatment over time, and we consider in particular the setting when multiple different treatments can be assigned at each time step. In this figure, we consider as an example estimating treatment effects for patients with cancer. These patients are often prescribed multiple treatments at the same time, which may include chemotherapy, radiotherapy, and immunotherapy. The assignment of these treatments at each time step depends on the patient covariates, in this case tumor volume and potential side effects such as hematotoxicity, and how these patient covariates have evolved over time. And the treatments are given with the aim of decreasing the tumor volume in this case. However, we notice that the combination of treatments assigned to the patient changed the time step 3 due to the increased side effects caused by the previous treatments. Now, given such observational data about patients, which can be found in their electronic health records, we want to be able to estimate individualized treatment effects. So, conditioned on the patient history of covariates and treatments, we want to estimate the patient outcomes, which in this case can be survival probability, under different combinations of treatments that are part of a future treatment plan. And all of the existing methods for estimating individualized treatment effects over time assume that there are no hidden confounders in the data. This means that we observe all of the patient covariates that are affecting the treatment assignment and the patient outcomes. However, as we will see, this assumption is not testable in practice. Moreover, the presence of hidden confounders introduces bias when estimating treatment effects over time. So, for example, consider that while the side effects are also affecting the patient's survival probability and the changes in the treatment assignments, they are not recorded in the observational data for the patient. So, if we use an observational data set that only has information about tumor volume and the treatment assignments, this will lead to biased estimates of the patient outcomes because these outcomes crucially depend on the side effects which are not in the data. So in this paper, we propose taking advantage of the dependencies in the multiple treatment assignments over time in order to infer latent variables that can act as substitutes for these hidden confounders. And these latent variables can then be used to augment observational datasets and subsequently obtain unbiased estimates of the treatment effects. In terms of problem formalism, we assume that we have access to an observational dataset, and for each patient, we observe time-dependent covariates and time-dependent treatments. At each time step, there can be k different treatments that can be simultaneously assigned to the patient, and this is very important for our setting. Moreover, we also observe the patient outcome yt+1 given the history of covariates and treatments. We work in the potential outcomes framework introduced by Neema and Rupin and expanded by Romis and Hernan to account for time-varying treatments. And we want to be able to estimate all potential outcomes, both factual and counterfactual, under an intended treatment plan that starts at time step t, conditioned on the patient history until time step t. Now, to be able to learn these potential outcomes from the observational data, we make the standard assumption of sequential overlap, which means that each time step, each patient has a non-zero probability of receiving each treatment. And very important, this assumption can be tested in practice. Now, all existing methods for estimating individualized treatment effects over time also assume that there are no hidden confounders. This assumption can be written in terms of the following conditional independence relationship, which states that the potential outcomes for any treatment plan starting at time step t are conditionally independent on the treatment assignments at time step t given the patient history. This assumption is not testable in practice since it requires a conditional independence of the treatment with all of the potential outcomes, both factual and counterfactuals. However, since the counterfactuals are never observed, it is not possible to test for this conditional independence. And if this assumption doesn't hold, then we will obtain biased estimates of the treatment effects. The problem of hidden confounders in a static setting has been tackled by Wang and Bley in the Blessing of Multiple Causes paper. They developed a theory for deconfounding, which means adjusting for the bias introduced by the existence of hidden confounders in observational data in the static causal inference setting, and they noted that the existence of multiple treatments makes this task easier. In particular, they observed that the dependencies in the assignment of multiple treatment in the static setting can be used to infer latent variables that capture these dependencies and render them conditionally independent. Then these latent variables can be used as substitutes for the hidden confounders. Now, inferring latent variables that can act as substitutes for the hidden confounders in the longitudinal setting is significantly more complex than in the static setting. This is not just because the hidden confounders may vary over time, but also because the hidden confounders may be affected by previous treatments and covariates. And in this case, standard latent variable models are no longer applicable as they cannot capture these time dependencies. For instance, consider again the case when the patient's side effects are not recorded in the observational data, and thus can be considered hidden confounders. The side effects are changing over time depending on previously assigned treatments, and they can also affect future treatment assignments. Thus, these hidden confounders introduce dependencies in the way the multiple different treatments are assigned over time. In this paper, we introduce the time series deconfounder, which is a method that enables the unbiased estimation of treatment effects over time in the presence of hidden confounders by taking advantage of the way multiple treatments are assigned over time. So the time series deconfounder relies on building a factor model over time to obtain a sequence of latent variables that can act as substitutes for the hidden confounders. Then these latent variables can be used to augment existing observational datasets and thus lead to unbiased estimates of the treatment effects. The first step of the time series deconfounder is to build a factor model that can capture the distribution of the causes over time. In this factor model, each time step t, the latent variable zt is built as a function of the patient history, such that, together with the patient covariates xt, it renders the assigned treatments conditionally independent. This enables us to build a factor model of the assigned causes that has a joint distribution as written on this slide, where theta are the parameters in the model. The factor model construction takes advantage of the dependencies between the multiple treatment assignments over time to build a latent variable zt. Through this construction, we can rule out the existence of other multi-cause confounders which are not captured by zt. Now, to understand why this is the case, consider the graphical model in the figure on the right. By contradiction, assume that there exists another multi-cause confounders, bt, not captured by zt. If this is the case, by this separation, the conditional independence between the assigned causes given zt and xt cannot hold anymore. So because of this, we can rule out the existence of other multi-cause confounders that are not captured by z. However, this argument cannot be used for single-cause confounders, such as lt, which are only affecting one of the causes and the potential outcomes. Because of this, we assume that there are no hidden single-cause confounders. And this assumption means that we observe all patient covariates that might affect the assignment of only one of the treatments. This assumption becomes increasingly weaker as the number of treatments increases each time step, and because the more causes we observe, the less likely it becomes for a hidden confounder to affect only one of them. We can then prove that the potential outcomes for any treatment plan starting at time step t are conditionally independent of the treatment's time step t, given the history of treatments, observed patient covariates, and infer substitutes for the hidden confounders. And this essentially gives us sequencer strong ignorability. And theorem 1 is proved by leveraging the no hidden single cause confounders assumption, the fact that the substitute confounders zt are inferred without knowledge of the potential outcomes y, and the fact that the causes ATP1 and ATK are jointly independent given zt and xt. This result means that at each time step, the histories of treatments, observed patient covariates, and latent variables contain all of the dependencies between the potential outcomes and the assigned causes, and thus can be used to reliably estimate individualized treatment effects. The theory only holds if the fitted factor model captures well the distribution of the assigned causes. This condition can be tested by extending predictive model checking to the time series setting. So we can compute p-values over time to evaluate how similar the distribution of the treatments learned by the factor model is with the distribution of the treatments in a validation set of patients. Moreover, it is also needed that the substitutes for the hidden confounder ct satisfy positivity, and this condition can also be tested. After fitting the factor model, we can use it to sample the sequence of latent variables from z1 to zt and incorporate them in the observational data about the patients. Then the time series deconfounder fits an outcome model to estimate individualized treatment effects over time. What we mean here by outcome model is any existing method capable of estimating treatment effects over time from observational data. In our case, the outcome model also needs to be able to handle the multiple treatment assignments each time step. In our paper in the experiment, we use marginal structure models and recurrent marginal structural networks as possible outcome models. Since we are dealing with time-varying treatments, we cannot use standard factor models such as PC or deep exponential families to infer the substitutes for the hidden confounders, as these were designed for a static setting. So using the theory developed for the factor model over time, we introduced a practical implementation based on a recurrent neural network with multitask output and variational dropout as illustrated in this figure. So we place Z as a function of the patient history, processed through a recurrent neural network. Then, use multitask heads with fully connected layers to model each treatment assignment as conditionally independent given the latent variable Z and the patient covariates X. To model the probabilistic nature of the factor models, we incorporate variational dropout in the recurrent neural network as illustrated in this figure. And using dropout enables us to obtain samples from ZT and the treatment assignments AT. These samples are useful for computing the predictive checks over time to evaluate the factor model, but also to estimate the uncertainty in the latent variable ZT, and then in the potential outcomes. And using the known treatment assignments from the observational dataset, this factor model can be trained using gradient descent-based methods. To validate the theory for a time series deconfounder, we perform experiments on synthetic data where we vary the effect of hidden confounding. It is not possible to validate the method on real datasets since the true extent of hidden confounding is never known. Now, to keep the simulation process general, we propose building a dataset with p-order autoregressive processes. At each time step t, we simulate k time-varying covariates xtk, representing single-cause confounders, and a multi-cause hidden confounder zt, as described in the following equations. The value of zt changes over time and is also affected by past treatments. Now, at each time step t, the treatment assignments ATJ depends on the single-cause confounder xtj and the multi-cause hidden confounder zt, where here hat xtj and hat zt are the sum of the covariates and confounders respectively over the last p time steps. And here gamma a controls the amount of hidden confounding applied to the treatment assignments. The outcome is also obtained as a function of the covariate and hidden confounder, where the parameter gamma y controls the amount of hidden confounding applied to the outcome. The observational dataset in this case consists of the simulated trajectories with patient covariates x, treatment A, and the outcome y, and we know that there are hidden cause confounders since Z is not included in this data. Using this dataset, we use a time series deconfounder to perform one step ahead estimation of the effects of treatments on the patient outcome. In the following figure, we illustrate the root mean squared error obtained for one step ahead estimation of treatment responses. We use the time series deconfounder together with two different outcome models, recurrent marginal structural networks and marginal structural models. So the way this works is that we first train the factor model to infer the substitutes for the hidden confounders, and then we use these substitutes to augment the observational dataset and then use this dataset to fit the outcome models. We control the degree of hidden confounding through the parameters gamma A and gamma Y, which we set to be the same in this experiment, and we vary them from 0, which means no hidden confounding, to 0.8, which indicates a high degree of hidden confounding. Now in this figure, the red lines show the results for training the outcome models with the generated observational data, which has hidden confounders. On the other hand, the purple lines show the results when also incorporating in the observational dataset the simulated, which are the oracle hidden confounders. The remaining lines show the results when applying the time series deconfounder. We notice that our method gives unbiased estimates of the treatment responses that are close to the estimates obtained using the simulated oracle confounders. And here dz indicates a size using the factor model for the latent variables that are inferred as substitutes for the hidden confounders. And notice that the method is robust to model misspecification, performing similarly when dz is set to 1, which is a simulated size of the hidden confounders, and also when dz is set to 5, which is a misspecified size of the hidden confounders. And this is important because in real data we may never know the true number of hidden confounders. Also, when the no hidden single cause confounder assumption is invalidated, namely when the latent variables zt are inferred after removing the single cause confounder x1 from the dataset, we obtain biased estimates of the treatment responses. However, the performance in this case is comparable to the performance when there is no control for the hidden confounders. And finally, we also perform an experiment on real data using the MIMIC database, from which we extracted a dataset with patients that received a combination of the following three treatment options at each time step: antibiotics, vasopressors, and mechanical ventilator. And for each patient, we extracted 25 patient covariates, consisting of lab test results and vital signs measured over time. In this experiment, the aim was to evaluate the effect of treatment on the following patient covariates: white blood cell count, blood pressure, and oxygen saturation. And hidden confounding is present in this dataset, as patient comorbidities and several lab tests were not included. However, since this is a real dataset, it is not possible to evaluate the extent of hidden confounding or to estimate the true oracle treatment responses. In this table here, we report the root mean squared error when estimating treatment responses by using marginal structure models and recurrent marginal structure networks outcome models directly on the extracted dataset, which is confounded, and after applying the time series deconfounder and augmenting the dataset with the substitutes for the hidden confounders of different dimensionalities dz. We notice that in all cases, the time series deconfounder enables us to obtain a lower error when estimating the effect of antibiotics, vasopressors, and mechanical ventilator on the patient's white blood cell count, blood pressure, and oxygen saturation. Causal inference relies on assumptions. So far, all existing methods for estimating treatment effects over time assume that there are no multi-cause and no single-cause hidden confounders. In this paper, we make the weaker assumption that there are no single-cause hidden confounders, and we propose a method that can be used to infer latent variables that can act as substitutes for the multi-cause confounders. However, identifiability of the potential outcomes using the deconfounder framework may represent a problem. When this is the case, the uncertainty in the potential outcomes can be used to assess the reliability of the time series deconfounder. In particular, when the treatment effects are non-identifiable, the estimates of the time series deconfounder will have high variance. And future work can explore developing a theoretical understanding for the identifiability of causal effects when using the time series deconfounder in the multi-cause longitudinal setting. To summarize, the availability of observational data consisting of longitudinal information about patients prompted the development of methods for modeling the effects of treatment on the disease progression in patients. Now, all existing methods for estimating the individualized effects of time-dependent treatments from observational data make the untestable assumption that there are no hidden confounders. In the longitudinal setting, this assumption is even more problematic than in the static setting, because as the state of the patient changes over time and the complexity of treatment assignments and responses increases, it becomes much easier to miss important confounding information. So in this talk, we introduce the time series deconfounder, which is a method that takes advantage of the patterns in the multiple treatment assignments over time to infer latent variables that can be used as substitutes for the hidden confounders. And through experimental results on both synthetic and real datasets, we show the effectiveness of the time series deconfounder in removing the bias from the estimation of treatment responses over time in the presence of multi-cause hidden confounders. As the reference to the paper can be found here, and additional references can be found on the next slide. Moreover, the code for the time series deconfounder is publicly available, so I encourage you to try it out. And thank you for listening.